So, good afternoon to all the course participants. So, today we have the fourth lecture and important lecture on GNSS, which is on the Global Navigation Satellite System, signal structure, and the data formats. So, today myself and Sri Ashish Joshi ji both will be covering this topic. So, as we have discussed in the previous lectures, so the basic signal structure of Navstar GPS includes the course acquisition code and the P code. So two types of codes are used, out of which the P code is modulated on the L1 and L2 carrier waves, both the carrier waves, so that the unnecessary corrections can be done for the authorized receivers, whereas for the civilian purpose, CA code is there, course acquisition code, and this we have already discussed, and 50 bit per second almanac and IIRS data is also being transmitted, which includes the chart of all the artificial GPS satellites and the instantaneous coordinates of the GPS satellites to the receiver, so that they can be used for the measurement of the pseudo ranges. Then L5 is a new frequency which has been added from the block 2F onwards. The current block is the third one which is going on, and in that third one block L1C has also been added along with the military code AM code. So this is the current structure of the Navstar GPS signal. Then this was what we have discussed regarding the comparative table for the GPS, GLONASS, Galileo and Vido. So we discussed the services given by GPS. So L1, L2 and L5 are accessible to the civilian users. See, earlier actually CA code, because initially when the civilian access to the GPS code was not there, that time also CA used to be there. So primarily the CA code is basically utilized for the purpose of the catching hold of the P code. So it is a part of the system which is even utilizable for the authorized receiver. So it's not that the CA code is available only for the civilian users and it is not useful for the P code users. In both the cases, CA code is used. Then the GNSS signals, they are transmitted either in the FDMA format, CDMA format or the TDMA format. So FDMA format was being used by the GLONASS earlier, which is frequency division multiple access codes, whereas the GPS was sending the codes in the code division multiple access system. So these two systems has been in use earlier. So once the concept of GNSS came in the 2006, then GLONASS also started giving the CDMA codes. So thereafter only the concept of GNSS actually got fructified. So same receiver can receive the signals from the GPS and the GLONASS as CDMA codes, and it can resolve the position. So even if two signals from GLONASS and two from GPS are available, the position can be resolved. Now this signal basically, as we have discussed, the IIRS data there in that, and the almanac also comes in the signal. So the location of the satellites is informed to the receiver so that the data can be processed. Then the amount of time elapsed for the travel, that is also embedded in the signal in the form of the T1 time when it starts from the satellite, and T2 is the time when it reaches the receiver. So that T1 is from the atomic clock and T2 is from the quartz clock. So that creates a discrepancy or synchronization problem because one is the quartz clock, another is the atomic clock. So that results into the clock bias. So we have four unknowns: latitude, longitude, height, and the clock bias. So we require minimum 4 signals to resolve them using 4 independent equations. So then it also includes the clock status and the correction parameters for different purposes like the tropospheric corrections, ionospheric corrections. So those kind of arrangements are also there in the signal. So the clear access or the course acquisition code, which is also known as the gold code, is a small code 1023 bit long. As already discussed, it is providing the standard positioning service to the civilian receivers, whereas it is also used for the purpose of the P code. So first the P code receivers also, or the authorized receivers also catch hold of the CA signal, and then they get hold on the P signal. So it is CA code is used in both the type of receivers. Now the anti-spoofing AS. AS is the process of encryption of the P code using a W key, and that results as a Y code. Now this L1 and L5 are also used for the interoperability between various GNSS systems, which has evolved over time. It's a quite long code, and it has 37 one-week segments. One segment is assigned for each satellite. So besides the CA code and P code, now we have other modernized GPS new signals, basically, which are modernized navigation signals. So in that series, we have L2C with the new CNAV code, and it has started from block 2 RM in September 2005, and it also has civil moderate code and civil long length code. So one is of 20 millisecond and another is for 1500 millisecond time period. So one is represented by a CM, civil moderate, and CL, the civil long. And this provides higher accuracy for the ionospheric correction. Now, as I have told earlier, the L2C and L1C both are in pre-operational testing phase still, although L2C is currently on sufficient number of satellites. It also has a higher strength. It is about 250 times stronger than the L1CA code. So in the anti-jamming it will be easier for the indoor applications also, because the strength is higher, so it will be able to survive within indoor environments also, and better than CA code on LV in case of the jammers also. L5 signal, which is also new signal from block 2F, it was tested as a demo in block 2RM also. However, its main launches are from 2009 onwards in the block 2F. It provides safety of life signal I5 and Q5, and this is specifically meant for anti-jamming features and indoor applications. Now, another signal is the L1C signal, which has started from December 2018 only, and currently there are 5 such satellites which can provide L1C signal. Again, it is all in the pre-operational testing phase, and its rate is 100 bit per second, and it's a relatively long code with more flexibilities as compared to the legacy navigation signal. So this is renamed as CNAV2. So as I've already discussed, that block 3 actually requires full hardware as well as software changeover on the ground stations also. So this navigation message also we have seen earlier. So the frequencies are being allotted by the ITU for various services to the various GNSS constellations, and the navigation message actually consists of 25 frames, where each frame is taking about 30 seconds to get transmitted, and each frame is divided into 5 subframes also, where the data block 1 is providing us the clock coefficients and the clock bias, whereas the data block 2, which has the subframes 2 and 3, they broadcast the ephemeris data. They have the coordinates of the satellites. Then data block 3 is there, which consists of the subframe 4 and 5. It provides the almanac data, that is the chart of the satellites. Chart, basically what we mean to say is the satellites which are there in the region of the receiver from where it is receiving the signals, and besides that the other satellites which are not visible, about their parameters also information will be downloaded in the almanac data. Whereas ephemeris data will only provide the positions which are the satellites which are sending the signal to the receiver. Okay, and they are providing the information in the real time. That is the broadcast ephemeris data, and some other special information as required. So 5 subframes actually take 6 seconds each. Thus one set of frame of 5. That means one satellite data download requires 30 seconds. So if there are 25 satellites, so we will require 12.5 minutes to download the almanac data, and that makes it in one way compulsory that baselines are short, then we should at least run the observations, or we should collect the data sufficient to download the almanac data. So anyway, minimum 20-30 minutes data should be collected. However, if you are collecting less, then at least you should see that the almanac data takes 12.5 minutes time, and that should be permitted to while collecting the data. So the information about all the satellites which are there, you can see they are available. These are the links to the site which is given. This is from the GLONASS. So on the same site you have GLONASS, BIDO, GPS. All the satellites are detailed as per their tabs. So the information about their almanac is available here. So this particular slide gives the almanac for the GLONASS data. All these things are transparently available. So this almanac actually enables the GPS to search for the satellites so that they can establish the connection. Okay, so sometimes cycle slips are also there. That means loss of lock is also there with the satellite. So again, it can connect. So that almanac data is required for that. Now, as I told, currently we have 3 IGS stations operational at Lucknow, STREC, then the ISC Bangalore, and the NGRI Hyderabad, and few more are coming up. Now, GLONASS has a little different design from the GPS, as you already know, as I have explained earlier, that GPS is using a 6-orbit system, whereas GLONASS and Galileo use the 3-orbit based system. There is a variation in the elevation also. In GPS, it was 20,000 100 kilometers. However, in this case, it is at a little lower elevation. It is 19,140 kilometer average height for the GLONASS, and the launches of the satellites for GLONASS has been done such that the one of the satellite has a, on the exact opposite end there is another satellite also. Okay, because they are currently sending the signals in the same frequency, same signal. So what happens that since they are in the opposite end, so the same signal cannot reach to the receiver from more than one satellite. Initially, actually, the way they have decided for the GLONASS, the frequency was 1602 megahertz for one satellite, and next one is 1602 plus 0.5625. For second, it will n will become 2. For third, n will become 3, and so on. So there were 24 frequencies which were used for the 24 satellite constellation in GLONASS, but then this radio frequency interference was noted in them, and because of that, later on, instead of 24 frequencies, it was decided that once the satellites are in antipodal position, so the satellites which are on the opposite side of the Earth, they will use the same frequency. So from 24 frequencies, they started using only 12 frequencies so that they can contain the RFI effect of the signals. So the signals do not get affected by that. Now the GLONASS is also providing position, velocity, and acceleration vectors at a reference post to compute satellite locations. So similar to the GPS, they also have some difference with the atomic clock used by GLONASS and the UTC time. So those things are taken care. The frequency ratio F2 by F1 is constant for all the lunar satellites. For the L1 and L2, that is equal to 7 by 9. The atomic clocks which are there on board, they are operating at 5 megahertz. So then coming to the Galileo, Galileo is also used in different type of signals like E1, E6, E5, E5A, E5B. So E1 is also represented as L1 also. So the carrier frequency waves are here. They are ranging from 1176 to 1575. E5A is also the same as the L5 band. So most of the satellite systems used in the navigation, either they have L1 as a common band between various services or L5 as a common band in the various services. So different combinations can be used for the interoperability of the system. So this also has about 30 satellites, 27 operational and 3 spare satellites using 3 circular medium Earth orbits. And these Galileo satellites are stationed at about 2322 kilometer at an inclination of 55 degrees. So for the open services, basically L5, that is E5A, L1 and E5B. These are used for the generic open source services for the general public. Now, since it has a higher inclination to the equator, so they are able to provide good positioning in the higher latitude areas also, similar to the GLONASS. So now this IGNOS we discussed in the SBAS lecture also. They are providing the differential GNSS corrections and phase measurements and in the RTK mode or the static mode, either through the internet or as well as through the satellite based links. So these kind of services are provided by the IGNOS Data Access Service. And currently the SBAS is using the GPS signal, and the IGNOS 2 will be using the GPS as well as Galileo. And it is using the GLONASS service also. So all the details of it are available on the website at the given URL. So it is giving the full details about the GPS navigation data, GPS L1 code measurements, GPS L2 code measurements, GLONASS data sets, and for the this Galileo measurements also, because IGNOS 2 will be using the Galileo measurements also. Then we have the IIRS satellite. So it has 3 satellites in the geostationary orbit, that is at 36,000 kilometers, and then 4 satellites are there in the inclined geosynchronous orbits. So this is also using L5 and S band. And L5 is, as I told, it is common with the E5A band of the Galileo or the L5 of the GPS. So interoperability is also maintained between IIRS and the GPS or Galileo. Now this and the new latest Android version, as I have told you earlier, so the API level 29 has packages related to the IIRS. So the smartphones which are receiving or which are capable of receiving IIRS signals, they can use the API in level 29 for their programming or app generation. Like MapMy India has come up with one of the apps for the mobiles having IIRS services. Now IIRS has L5 and S band as allotted by the ITU. Third frequency also we are hoping to receive from the ITU near somewhere near L1, because then in that case what will happen, that we will have a better interoperability with the other system, because some systems have interoperability in L1 and some systems have interoperability in L5, but currently we are using the L5 and S band. The interface control document, Signal in Space ICD, has already been released, and the revised version is also released and that can be seen, and we will discuss it further in the dedicated lecture on INSS. So this depicts the bands where we have IRNSS, Galileo, GPS, and S-band of IRNSS also, because S-band is not used by any other system except that of the IRNSS. We hope to have some advantage by using S-band also. Quasi-Zenith satellite system also from Japan. It's a regional navigation system for Japan, and it began its launches in 2010 using highly elliptical inclined orbits using the Mitsubishi satellites, which are inclined at 45 degrees. Now this has a GPS interoperable free signals for the public, whereas the high performance signals, that is corrected signals, SAF and LEX, are chargeable. LEX, that is LEX interoperable, the LEX is also interoperable with the Galileo. So basically again you will see L1 and L5, they are used here for the interoperability with the other GNSS systems. QZSS is actually using the Japanese geodetic system. Again, this is a system which use GRS-80. GRS-80 is the nearest ellipsoid which has been in earlier use to that of the WGS-84. So GRS-80 and WGS-84 actually has very less difference, and this is creating an offset of about 2 centimeter actually, 0.02 meters, about 2 centimeter offset is being actually there between the two, GRS-80 and the WGS-84. Now coming to the BDO system, so they have 5 satellites in the geostationary orbit, then 3 inclined geosynchronous orbits, and 27 in the medium Earth orbit. So basically, like that, they have about 7 orbits in which they have placed all the satellites. Till now, actually, we have from testing to till today, they have almost 50 satellites in this phase, and we have now they have a large number of options. So they are able to provide open service with an accuracy of 10 meter and timing with an accuracy of 20 nanosecond and velocity at an accuracy of 2 centimeter per second. So it is also providing service to the general users, commercial services, and the restricted users. Then position is coming in the different type of formats. When you will use the GPS, you can use degree minute second format, or degree minute second decimal, degree minute decimal, or degree decimal. So that you can select when you are choosing the different options. Some of the understanding regarding the projection should also be there when we are using the GPS, because we have to do different type of settings. So either we can do it in the geographic lat long to make it simpler, or if many of us are using it in the UTM zone also, so we should have the idea about the UTM zone numbering system also, so that we can feed in the correct number for the survey, because each UTM zone has a separate origin. So best way is that you can do this task later. First you can do the survey in the geographic lat long itself. Well, after processing and mapping time, that time you can change the UTM zone number. So projections can be changed later also. Then for GNSS receivers also, like we are using Trimble, Leica, and other systems are there with us. Spectra Precision is there, Sapton Trio is there. So there also we have different type of formats are there. So we are receiving the data either in the .dat format or .t01, .t02, .gps. So these are some of the formats in which we are receiving. So all vendors or all have their own proprietary formats for storing the data. Now we are processing the data sets in Spectra Precision, that is from the earlier it was Trimble Business Center. Actually now the two companies have been merged. So we are using precision, spectral precision. So it has a project file with a extension of .vce. So this is one of the setup. So we have a base station in the center, and then we have occupied various rover locations because we were using two GNSS receivers at that time. So one was at base and another was used as a rover station. So these has been resolved using the spectra precision software. If you want to use it in another software, then we use Rhinex conversion also, random and dependent exchange, because this is like ASCII code. So this can be used by any of the softwares. So if you have multiple GNSS receivers which belong to different vendors like Trimble, separate Trio. So in that case, all the datasets from their proprietary format can be converted to the Rhinex format using the conversion utility which is shown here. So there we have to just open the file which we want to use and choose the format of the file, select it, and then we can run the process for conversion, and the Rhinex file will be created. And all the datasets from various GNSS receivers can be brought to a Rhinex file, and then it can be processed together. Now, in the standard procedures, what we are doing with the commercial softwares, we require much less effort actually. So we normally import the rover data and the base station data, and we directly process it, either with the native format or with the Rhinex format. But for some high-end processing, the other formats are also available, and we can download the IGS station datasets also, either as SP3 files. Then for tectonic measurements, we need to take care of the precision and rotation also. So IIRS, International Earth Rotation Service, and International GNSS Service formats for the exchange of Earth orientation parameters, they are also required. So these files can also be downloaded and can be used in the processing. So usually in the commercial systems, we are not using these, but for some of the crystal deformation studies and high precision studies, these are required. Then there is a solution independent exchange format for exchange of solutions and of the meta information. So Synex is also one of the formats in which data is available. So there is a troposphere Synex, which is providing information regarding the troposphere. So the respective links for the different type of data sets are given here. Then antenna exchange formats are also there for the receiver and the satellite antenna information. So these either we have to have correct information, or we may need to upload it or update it. Similarly, for ionospheric correction, we need ionospheric model exchange format, INX, for the ionospheric maps also. So these all different type of informations are coming in different formats, and we require all of these at the time of high precision processing, either in the Bernice software or in Gamut software or GLab or Article Lab. So these softwares require all these files for the purpose of very precise processing. So clock data is also coming in the Rhinex format for the exchange of satellite and receiver clock information. Now these various websites are there for the crystal deformation as shown here, and different datasets can be found here along with the details of the datasets, how the data has been shown in them. Now here I would like to show that in the new formats, like in this antenna format, antenna file, INSS is already there, because now Rhinex format has been updated, and there is a space for the INSS satellites. So that is one thing I would like to tell. Then there is an inter-service data integration for geodetic operations, because as the verification of GPS results basically are done against the satellite laser ranging SLR station. So when we have tested the GPS data with the SLR methodology, then we have found that absolute corrections are possible up to 15 to 20 centimeters. So that kind of accuracy we can achieve from the DGPS operations. And the similar other services are there, like the very long baseline interferometry. So all these techniques like laser ranging service is also there. So they require a very definite management of data sets from different sources. Otherwise, it will be difficult to process these data sets. So all these things are available in respective places, which are not regularly required if we are working with the commercial software. But if we are working with the scientific software, then this will be required. So these are the location of different space geodesy instruments for various purposes, like CORDS are there, IGS stations are there, VLBI stations are there, then laser ranging stations are there. So these are the locations. Doris is there. So different types of files are also there. So I have just listed them. For the Earth orientation parameters, we have UT1.pol files. Nutation tables are there. Lunar solar ephemerides are required. GPS time and UTC time, because this is a dynamic factor. Because of the nutation and precision of the Earth, the difference between the GPS clock and the international atomic time, which we are referring as UTC also, the difference is not static. So that difference also has to be compensated. So similarly for antenna and receiver, the dimensions of the antenna and mechanical these receivers and the antennas, that all has to go as an input for the purpose of the processing. Similarly, for the troposphere and ionospheric corrections, as well as ocean loading, atmospheric tidal loading, and non-tidal atmospheric loading also. So there is a lot many formats which are there, which actually may be required for some of the critical applications. And some of these observations are coming from the meteorological stations, which we have installed either with the IGS stations or the CORS datasets. So they are also being utilized. So when we are procuring the GPS for the utilization in the IGS station or the CORS stations, MAT packages are also procured with them. So this shows the because this utility is important actually. So I just have displayed here the page from where the utility for the RINEX data conversion can be downloaded. Once you download this utility, then you can convert the data from any of the proprietary format to the RINEX format, which can be used for the processing further. So similarly, different tables are there which explain the representation of different type of data sets like time, date, month, then Julian day, and then which information is coming from the GPS. That, like in this case, that data type, and at various places in the header files and the inbuilt data, you will have representation of GPS observations by GEO, Jonas observations as RO, Galileo observation as EO, and so on. So all this kind of and much more actually, lot of formats are there which are required to be understood if we go for the advanced processing. And we have a dedicated lecture for advanced processing next week, which you should not miss at all. Okay, so there are the use of all data sets and the extensions which we have done now, that will be covered in the lecture on the advanced processing. So I will stop here, and then further my colleague Shri Ashish Joshi will continue with the description of the internal data. So Ashish ji, you can share your screen now.
Yeah.
Thank you.
Thank you, Ashutosh sir. Myself, Ashish Joshi. I am working as a scientist at Photogrammetric and Remote Sensing Department, IIRS. Today I will give the lecture on the GPS receiver data formats, which include the RINEX and precision ephemeris. So what is the RINEX data format? Actually, it is a GPS receiver data format. The full form of the RINEX is the Receiver Independent Exchange Format. It is developed by the Astronomical Institute of the University of Berlin in 1989. Actually, earlier all manufacturers have developed their own proprietary file format specific to their receivers and processing software. So there is a problem occurring when processing data from another manufacturing receiver. And there is also requirement of the easy exchange of the raw GPS data. And if we will have the multiple software, so the processing across the different software, a common format is required. So keeping in mind all these problems, that University of Bernese developed a common format which is called the RINES format. So in 1989, it is the first version of the RINES was accepted. Then after some modification, in 1992, version 2 was released with certain updation and modification like 2.1, 2.11, 2.20. And finally, in 2007, the version 3 is formed with significant changes. And the recently version is 3.05, which was released on the December 2020. So according to the versions, we have different files in the RINES format. So RINES version 2.0 consists of the 4 ASCII files. This consists of observation data file, navigation message file, meteorological data file, and GLONASS navigation message file. So this is the version, initial version, version 2.0. After that, some updation has been occurred. Then the RINES version 2.10 and 2.11 consists like 6 ASCII files. This consists the observation data file, navigation message file, meteorological data file, GLONASS navigation message file, geo navigation message file, and satellite and receiver clock data file. So these are the versions, and we have different files in every version. Then finally, in the version 3.0, all unnecessary files has been deleted, and mostly it consists of the 3 files. One is the observation data file, second is the navigation message file, and the third is the meteorological data file. So what these files will contain? So observation data file majorly consists of the GPS measurements, which include the pseudo range. And second, GPS navigation message file is consisting of the ephemeris or the orbit information. So the observation file consists of the pseudo range means from the GPS receiver to our points. What is the pseudo range? So that is in the observation data file. In the navigation file, we have the ephemeris. Ephemeris means we have the x, y, z, which is called the position, and x dot, y dot, z dot, which is called the velocity, and with time stamping. Okay, so that is the navigation message file. Another file is the meteorological data file. It consists of the pressure, temperature, relative humidity, etc. Okay, so in this lecture, we mainly concentrate upon the observation data file and the GPS navigation message file, because we are dealing with the position of a point. So we will deal with the 2 files, which is called the observation data file and the navigation message file. So first is the observation file. So what is the observation file? The observation file includes the 3 fundamental quantities. What are they? First is the time, second is the pseudo range, third is the phase. So time is the receiver time of the received signals. It is expressed in the GPS time and not in the universal time. Okay. And what is the pseudo range? It is the distance from the receiver antenna to the satellite antenna, including receiver and the satellite clock offsets. And the unit of the pseudo range is in meters. And the phase is the carrier phase measured in the whole cycles. So basically in the observation file, we have the 3 fundamental units, which is called the time, second is the pseudo range, and third is the phase. So first we will look about how the RINES file format look like. Okay, so how to name the RINES file. Okay, so we will start with if this is the file name. So but each character will identify the files. So first 4 characters, it will represent the station name. Okay, so if the receiver GPS receiver at the IIRS campus, then we can rename it as a station name IIRS. Okay, the 3 character will represent the day of the year. Okay, so means if today's date is 17 September 2021, so we will convert this date into the day of the year. So day of the year is coming around 260. Okay, so after that the file name is first 4 is the station name, then another 3 character will contain the day of the year, it is 260. Okay, after that the F, it will represent like it is a daily file or it is the hourly file. So if it is a 0 convention, then it is a daily file. Otherwise we have other convention like A, B, X. Okay, so for the, if we are considering like it is a daily file, means in a 1 day 1 file, then we will consider as 0. Okay, after that what is there, 2-digit year, means what is the year. So if we have the 21, then it is the 2021, we have the 21. Okay, and after that the last is the T, means what is the type of the file. So if we are considering it is a observation file, then it is the O. If it is a navigation file, then it is the N, and meteorological file, it is the M. Okay, so by this convention we can name any file. So if we keeping in this mind, we will generate our own Rhinex file like IIRS, means it is the station name, 260 is the day of the year, and 0 is the, it is a daily file, and 21 is the, it is the year name, it is 2021, so last 2 digit 21, and N is for the navigation message. And similarly for the observation file, we have to replace by O. So this in this way we can generate the name of the Rhinex file. So what are the observation codes in the Rhinex file? Okay, so in different versions we have different codes. Okay, so if we are considering like Rhinex version 2.0, then we have these codes, means L1, L2 is there, C1 is there, P1, P2 is there, T1, T2 is there, and T1, T2 is there. Okay, so what is L1, L2? It will consist of the code of the phase measurement. C1, it will have the pseudo range using the CA code. Okay, P1, P2 will consist of the pseudo range using the P code on L1, L2. So based on these codes, we will find out our measurements. Similarly, in the Rhinex 2.10, we have different codes. Here we have the S1 and S2 is also there, which includes the raw signal strength or SNR. Okay, so in this way, we have some observation codes in our Rhinex format. Based on these observation codes, we will identify our value of that signal. Likewise, in the Rhinex version 2.11, we have the different satellite combination. Okay, like for the if we have the GPS satellite constellation, we have these codes. We have the GLONASS, then G1, G2 are the frequency band codes, and Galileo, we have these codes, and ISRO system, we have these codes. Okay, so each codes will have the different characteristics, like C1, P1 will represent the pseudo range, and L1 will represent the carrier phase, D1 is for the Doppler, and S1 is for the signal strength. Okay, so for the different Rhinex version, we have different observation codes. So this is the latest version 3.0, which was released on 2007. Then we have this different codes for the GPS, like L1, L2, L5 for the GPS, and different codes for the different constellations. So this is the for the GPS. Similarly, we have the observation course for GLONASS, Galileo, and ISRO also, like this one only. So this is the RINEX version 3.0. After that, we have the updation in the RINEX version also, and latest in the December 2020, we have the RINEX version 3.05. But the basic course are like that one only. Means understanding point of view, we have to understand in that way only. So we should have one format, and from that format, we have to map our values. So in this case, if we are as an example, we can see this is the RINEX 2.10 version. Okay, so earlier in a previous slide I have shown you, this is the observation ports for the version 2.10. Means L1, L2 is the measurement on the L1 frequency and L2 frequency. C1 is the pseudo range using the CA code on L1. P1, P2 are the pseudo range using the P code. D1, D2 is the Doppler frequency. T1, T2 is the transit integrated Doppler, and S1, S2 are the raw signal. So these are the codes for the version 2.10. Now, if we will get the RINEX file of version 2.0, so we will find these type of values. So from there, what we will see, what are the codes. So these are some of the codes: L1, L2, P1, P2, C1, S1, S2. Means this file will contain these values. Means it will contain the L1 means phase measurement on L1. Means L1, L2 will represent the phase measurement. P1, P2 will represent the pseudo range. C1 it will represent the pseudo range using the CA code, and S1 and S2 will represent the signal strength. So from the observation code, we will know these are the values we can derive from this file. So these are the codes, and these are the actual values. Okay, so these are the codes, means these are some of the values. So first value, so it will L1, L2, and these are the pseudo ranges. So 1, 2, and 3 pseudo range, and this is the S1, S2, it is the signal strength. Okay, so this is the data section, and this is the header section. In the header section, we have the observation code, and then the data section, we have the actual values. Okay, so this is the ASCII file, RINEX format of version 2.10. And again in detail, we can see how the data section will look. So this will consist the time, and 8 is the how many satellites are there at that time. It is number of satellites are 8, and this is the satellite number. So from which satellite it is coming. So this is the satellite number, and after that this is the observation data. So this observation data will contain the phase, it will contain the pseudo range, and the signal strength. Okay, so this is the RINEX format for the observation file. Now second file is the navigation file. So from the observation file, we are mainly getting our parameter like pseudo range. Okay, but we will need the satellite positions also. So how to get the satellite position? So that satellite positions are derived using the Capillarian elements. Okay, so every navigation file contains these 6 capillary elements, which includes the semi-major axis, eccentricity, argument of perigee, inclination, right ascension of ascending node, and true anomaly. So these are the 6 Capillarian elements. Through these 6 Capillarian elements, we can derive our position of the satellite. Okay, so these are some of the elements. Means this semi-major axis and eccentricity will tell about the size and shape of the satellite orbit. This omega will tell the argument of perigee, which represents the orientation of the satellite orbit. I is the inclination, which includes the orbit plane in the equatorial system, and the term which is called the true anomaly, which will represent the satellite position in the satellite orbit. So these are some of the parameters of the Capillarian elements. So in a diagram, we can show this is the equatorial plane of the Earth, and this is the satellite orbit plane. Okay, so at the point where it intersect, it is called the ascending node. Okay, so if this is the ascending node, and if this is the x-axis, which is looking towards a fixed star, and this z-axis is the towards the North Pole, and this cross product of these two axes will give the y-axis. Okay, so what is the our angle, which is called the right ascension of ascending node? It is the angle which is making by the which is made by the ascending node with respect to the x-axis. So this is the RAN. And what is the argument of perigee? Argument of perigee is the angle which the this ascending node made with respect to the perigee point. Okay, and what the our true anomaly? True anomaly is the angle which the satellite makes with respect to the perigee. Okay, so these are some of the parameters of the Keplerian orbit. So apart from these 6 Keplerian elements, we have other parameters, derived parameters. So in the navigation file, we have total 16 parameters. So 6 are the Keplerian elements, and other derived parameters are the rate of the right ascension, rate of the inclination, and correction to the argument of latitude, and other parameters. So total 16 parameters we have in the navigation file. So this is how the navigation file will look like. So this first part is the header section, and second part is the data section. So our data section in the navigation file is divided into like this. So basically, if we divide this point, so this is called the mean anomaly, eccentricity, this is called the semi-major axis, this is the RAN, this is the argument of perigee, and this is the inclination. And other parameters are also useful, but these 6 parameters we can make any satellite orbit with the help of the Keplerian elements. So if in the in previous slide, the navigation data section of the navigation file look like this. So from their data section, we can derive the time from there, eccentricity, mean motion, and mean anomaly, and that is semi-major axis, and this is the RAN, and this is the argument of perigee, and this is the inclination. Okay, so from that file, navigation file, we can extract our Keplerian element, and from the Keplerian elements, we can derive the state vectors of a orbit. Means we can make an orbit from the Keplerian elements. Now we will use this equation: r is equals to square root of x minus xz square plus y minus yz square plus z minus zz square. So this r means it is a pseudo range. It will come from the observation file, and this xz, yz, zz, which is called the position vector of the satellite, it will come from the navigation file. Now if we have these three we have this equation, and we have multiple observations coming, we can solve this equation and we can derive the xyz. Means we can know the position of the GPS receiver. Okay, so if we have the 4 points, and 4 points are used to derive the and to solve this equation and to derive the xyz position of a GPS receiver. Okay, so these are the some concept of the navigation file and the observation file. So from that Rhinex format, we have derived the satellite positions. If we have got from at a Bangalore GPS receiver, so we have this satellite positions. So we have plotted in the MATLAB the different satellite position derived from the navigation message file. So this are how these 7 satellites are spread at a particular time for the GPS receiver at Bangalore. Okay, so this is the visualization of the different satellite position at a particular time. Now that Rhinex format is particularly we have in the GPS receiver. We can get this Rhinex format file from the GPS receiver. So it has the navigation parameters based at that particular time. Okay, so that are not exactly precise. So what we have to do, we have some precise ephemeris provided by the agency which is called the IIRS, which is also called the International GPS Service for Geodynamics. So first, this IGS is a voluntary federation established in 1992. After that, in 1999, it was known as the International GPS Service, and 2005, it is known as the International GNSS Service. So these this institute actually provides the precise ephemeris for the for getting our precise positional from the GPS data, because the RINES will contain some orbit parameters which are not so precise, because they are giving in the capillary elements, and only we can project, means we can make a satellite orbit which is not so precise. So this IIRS is providing the satellite state vector at a particular time, so that we can correlate these precision ephemeris with our data, and we can interpolate at a particular time a more precise satellite state vector, and from that satellite state vector we can get more precise positions of our GPS receiver. So IGS, what are the IGS products? It will provide the satellite ephemeris, means XYZ, XZ, YZ, Z dot, and time, and GLONASS satellite ephemeris, and the Earth rotation parameters, IGS tracking station coordinates and the velocities, GPS satellite and IGS tracking station, zenith topographic path delay estimates, and the global ionospheric maps. So these are some of the IGS products which it will provide at a particular time. So that precise ephemeris will provide at particular time. So based on the time interval, we can categorize different products. Means when we have the broadcast, so it has the latency of like it can provide in the real time. So the orbit accuracy is lesser, like it has the 160 centimeter inaccuracy in the orbits, and after 4 times a daily we have the orbits of 10 centimeter, and after 3 hours 4 times daily we have up to 5 centimeter accuracy, which is called the ultra rapid, and rapid is around 5 centimeter, and the final we have less than 5 centimeter, and satellite clock wires also up to the nanosecond. Okay, so based on the latency we have different products, and as the timing is improving, we have the better accuracy in our final products. Like we have the better orbit accuracy also, and we have better satellite clock accuracy also. Okay, so what we have to do means, in the IGS satellite IGS website, we have to go to our particular time. Means we have at particular time and day we have the RINES data file. So for that particular time or day, we have to go to that IGS website, and for that we can download these precision ephemeris. So these precision ephemeris will contain the time and the state vectors. So, and these are some of the products, which is called the final product, rapid product, and ultra rapid product at a particular time interval. And this is the website where we can download our precise ephemeris. So how the precise ephemeris will contain? So basically it will represent in the SP3 format. So what is the SP3 format? It will also contain the one is the header section and one is the data section. So in the data section, the first we can see this is the state vector time. So at this time it has these positions. Okay, so we have different positions at a particular time. So if we have the this state vector times and time intervals of 15 minutes. Okay, so after every 15 minutes we have the satellite positions. Okay, so this is the state vector, this is the X, Y, and Z, and this is the clock error, and this is the standard deviations. Okay, so from that precise ephemeris we can have the X, Y, Z positions, and these positions are actually contained in the ECEF coordinate system. So at a particular time we have this positional values of the satellite. So we have at a particular 15 minutes, we have this orbit. Okay, so for a particular one satellite, we have the precise ephemeris SP3 files. Okay. So if we have, these are different positions. So what we have, if we have any RINEX format file, so for a particular date and time, we will download this SP3 file, and from this SP3 file we get the satellite position at particular time, and we have one particular time in our RINEX data file also. So we have to interpolate the satellite position at that time, and that we can use to derive the correct GPS position. So these precise ephemeris file will help in getting the precise GPS coordinate with the help of the precise ephemeris. Okay, so that's all in my presentation, which contains the RINEX data format and the precise ephemeris. Okay, thank you. You can post your questions.